let's just give everyone just a couple moments to drop on in, because we are a live broadcast. We want to make sure everyone has an opportunity to sync on in. Wrapping things up today. Boom. Okay, that should be enough time. Welcome, tech artists from around the world. It's Friday, and it's 12:30, and it's time for another episode of Tech Art Talk Live. My name is Chris, and I am going to be your host for today. Well, guess what today, folks? We're wrapping things up. Okay, we've spent the last couple of months learning all about HLSL, learning about rendering, learning about the rendering pipeline. We've learned about how to do basic shading for all the way from simple textures all the way up through Phong and blend Phong lighting. Then we went into visual effects, and then we finally finishing things off with shadow maps. And today is the day where we wrap it all up, where we finish our shadow mapping. Now, we've started with things. Let's go right on to, let's just get right going with the shadow mapping here. All right, so we're working with the shadow mapping, but, oh, there it goes. Yeah, that would have been strange. Okay, so hopefully we saw that. Okay, we said that shadow mapping is done in 4 easy steps. Now, 2 weeks ago, we started talking about projection mapping, and then we showed how projection mapping can be used to project a shadow from a light onto a surface via a separate texture. And then last week, we started dealing with occlusion, and then we introduced the concept of depth mapping. And depth mapping is we actually render the scene from the perspective of the light and then capture all of the depth information of the scene and then put that into something called a depth map. And that depth map is going to be used this week for section 3 on how to take that information, and then from the distance of the light, we're actually going to share the distance from the objects, either from the shadow map or the object in front of it. And so objects in front of the shadow map are going to get called out. And then that's what it basically is, what is projection with occlusion testing, is the objects in front of the projection are going to call out the actual shadow. Okay, and then we're going to turn that around. It's almost the exact same algorithm, and we're going to actually make real projections of where we're going to kind of like inverse that entire process, and then we are going to create the shadows out of that which was occluded out. Are you with me so far? Okay, if you're not with me, no problem. We're going to go over that again real quick. All right, remember 2 weeks ago we showed how to examine your lights, and your lights are no longer just light emitters. They can actually be potential shadow emitters, and that's what they are in the scene. Your shadows are going to get projected from your lights as if they were actual projectors. And so lights are very good at projecting any kind of shape, but we're going to stick with a texture. And what we did 2 weeks ago is we showed how to project a texture from the light onto the surface of our object. Remember, remind you, we are rendering the surface of the object, so this does have to be part of the surface rendering, but the actual texture map is being projected onto the surface. And so that's why it has to be in NDC space. All right, now then last week what we started to deal with is occlusion mapping. And so in this situation we have our light object casting a shadow right onto our teapot here. So how do we identify what is actually going to be on the teapot and what's going to be on the background? And we're going to have to use occlusion techniques, or we're going to have to borrow in some depth mapping. Now, what is depth mapping? Depth mapping is where you've got a pre-render of where the entire scene gets rendered from the perspective of your light, and the objects that are closer to it will appear brighter, and the objects that are further away from your light will appear darker. And so you're going to have a nice gradient of objects that are right in your face. They're going to really appear white, and then the objects that are actually very far away are actually going to appear as darker and more transparent. Okay, so that rolls on to where we are this week, and what we're going to do is combine the projector texturing mapping and the depth in order to create occlusion testing. Now, occlusion testing is inside of the actual shader of our, instead of just projecting the shadow map coming from the light, what we're going to do is we're going to take that value and we're going to put it aside. We're going to then take the depth map, as a separate texture, and then we're going to look at that. Then we're going to look at the object that we're rendering, and then we're going to say, okay, look at this. We want the actual depth of the object, and we're going to compare that to the depth of the pixel at that size, at that location of the scene. Remember, we're going to be projecting that from the light, so we're projecting it, so there should be a one-to-one parity. Then we're going to compare our pixel depth versus the sample depth. Now this is where we identify if something is closer to the camera or not. If the pixel depth is less than the sample depth, then we're just going to return white. And if we return white, then that's fine. Then that means our projected shadow map is just going to be normal. And so that means that our object being rendered is closer to camera. However, if our pixel depth is greater than our sample depth, then that means that the sampled object is closer to the camera than the pixel depth. And so that means that it's going to be, we're just going to render the actual contents of that original projected texture. And then that original projected texture, I kind of cheated. It's black and it's white, and so therefore it's either white or it's black. And so basically what we're going to be projecting is black, and white is just going to be transparent. So we kind of cheated with that. It's not a colored texture, so we kind of hedged our bets a little bit. But regardless, the results of the texture map then are going to be multiplied against the screen rendering of our color. Now there is one little problem with just doing this simple little test, and that's something called shadow acne. Shadow acne is where it's an aliasing issue. And the aliasing issue is sometimes the shadow map, because it's not always that big, sometimes the shadow maps can be kind of dinky. They might actually be as small as 128 by 128 or 256 by 256, and the shadow map is just too small. And when you're juggling and comparing the shadow map depth versus your object depth, the resolution may not be good, and it might be the depths might be kind of quantized and look kind of chunky and produce kind of unpredictable situations. So we're going to end up with ugly looking images here. If we look on the image on the right, we see a nice clean image, and on the left we have a situation of where the shadow is the depth is really having a hard time, and it's going to create this kind of shadow acne, or this kind of these unpredictable artifacts that just kind of come out of nowhere, and it looks like garbage and it looks like noise. Okay, there are several solutions about it. 3 solutions in precise that I want to talk about. And the first one is the technique that I'm actually employing in with this lesson here, is that we're going to be biasing the depth by some kind of amount. Okay, what does that mean? Is that we're going to take our sample depth, and then we're just going to add or subtract a little bit of a bias. And so that is sufficiently enough to always send the shadow comparison off to one side or the other. Now, if you get into more sophisticated shadow map rendering, you actually deal with something called slope scale depth biasing, where you actually are taking the slope of the geometry in respect to the camera and look at the angle of the polygon compared to the camera, and that angle should create a certain gradient that causes the shadow to behave a little bit differently. And so you're taking this very complicated mathematical calculation and using that in order to calculate what your depth bias is. We're not going to be going into that. That's a little bit too long-haired for this lecture here. But a third technique is dealing with the cull front-facing geometry when rendering the depth map. And so what that means is we are dealing with the we're just not going to deal with at all. We're just going to cull out the front faces. So we're only going to be dealing with the back faces when rendering the depth map. So that helps remove some of the stuff that's closer to the camera, so we're not even going to deal with that geometry. Now, once again, that is kind of a hack. It doesn't work all the time. It might work, it might not. And so that's why we're choosing the depth bias in order to complement this lecture, because it makes just a little bit more sense. Okay, so let's take a look at the demo that we're going to be dealing with here. All right, so remember 2 weeks ago we brought into the concept of the shadow mapping. So as you can see here in our situation, basically the viewer is where our light is, and our light is projecting the shadow of the skull, or the texture of the skull. You see it's just really just a black and white texture. It's being projected onto our surface. And we know that this is a projected surface because if we wanted to, we could move our camera around and we see that it's projected onto the surface there. And so it goes off and under, and if we turn around, there it is, and we see that it's projected all the way through. All right, so last week what we did was we brought in a concept of depth mapping. So we're going to include, if we can see this, we're going to render a teapot object. No, that's it here. Oh, there it is. There we go. There it is. We're going to render a teapot object. There's our teapot. And now we're going to render the scene from the perspective of the camera. And so the camera is going to look at that scene and say, ooh, I've got a teapot in here. And the closest parts of the teapot then are going to render off as kind of a little bit brighter white. And the parts of the teapot that are furthest from the camera are going to appear darker and more transparent. And let me see, we have a little bit of depth here. Yeah, as you can see, as we bring the teapot really, really close to the camera, then it starts to get really, really bright. Okay, we're going to use that information, that depth information, to compare against the depth that we're actually generating from the scene in the actual render. And that's what we're going to do here. And let's go on up to right here. And so what you see here is the actual occlusion testing. So notice that our teapot is right here, and it's carving a hole right inside of our projection map. Okay, so what is this? How do we actually go ahead and implement this? Let me make this a little bit bigger. Come on. Let's go. Come on. Okay, that's all it's going to prepare today, so I don't think we're going to get any big. So inside of our surface shader, it's no longer just robust enough to handle just the shadow projection. We do have to deal with more issues. And so for this, I'm going to need to define what my color white is and my color black is. And that's real simple. Color white is just ones right across the board. It's a float 4 returning 1, 1, 1. And a black is black across the board, of course, except for the 1 inside of the opacity, where it defines that this is an opaque bias. And now here is our constant float. This is our depth bias. Notice that it's not very big. It's 0.005. It's big enough in order to create a discrepancy of where we can make sure that the depth bias is the right size. Now, depth bias is a difficult parameter, and I don't want, and if I don't mention this now, I think I'm going to forget. But I wanted to make sure that we talked about this now, because if your depth bias gets too big, what we have is called a Peter Pan effect. And the Peter Pan effect is that it'll offset the shadow just a little bit in just such a way that it'll appear as if your character is floating. Kind of like Peter Pan. You remember in the Peter Pan movie, Peter Pan was flying around there until he lost his shadow, and then it wasn't until his shadow was reattached to him that he knew he was grounded again. And so that's what we have to do here. If your depth bias gets too large, then your shadow becomes disjoint from your character, and it looks like they're flying around. All right, now we've got our C buffer per frame, and this hasn't changed at all. This is the exact same contents that we had 2 weeks ago when we introduced the concept of the projection mapping. The only thing we added in here is the shadow map size. And the shadow map size is just a constant that we're going to be getting from the input from the user, but by default I'm going to be putting it as 512 by 512. Okay, our C buffer per object, this is going to stay exactly the same that we were using 2 weeks ago when we were working on our projection matrix. We have our world matrix, our specular color, and our specular power, and then our projective texture mapper. Remember, every single object has to have its own projective texture mapper in relationship to the light that's casting the shadow. All right, now we have our C buffer per scene, and then this is going to be our world light view projection. Remember, this world light view projection is created by the texture, by the light, and this has to do with the world the world view projection put onto the light, but then we also have to multiply our scalar matrix against this in order to get it to work properly and put our object into the proper ND&C space. Okay, now we have an extra, we have our color map, which is the checkerboard. We have our projected texture, which is our skull, and now we have our depth map, which is coming from what we created last week. And for every one of our textures, we're going to have a separate texture state. Notice that for our color sample, we're going to be doing just wrapping around the border, but for our projected texture sampler, we're going to use border, and that means border is that whatever the border of the texture map is, we're going to just maintain that color. And notice that we want the color white on this. And likewise, we're going to use that exact same texture map sampling for our depth map. It's also going to have border addressing for the address U and the address V, and its border color is going to be white. All right, and let's take a look at our data structure. Now, our data structure for the vertex shader going inside, nothing's changed from 2 weeks ago. Everything is exactly the same. And our vertex shader output, exact same that we created 2 weeks ago. Nothing is different. From our vertex shader, we're going to get our position, we're going to get our normal, our texture coordinates, our world position, our attenuation, and then we're going to get our projected texture coordinates. So nothing's changed 2 weeks ago. We're not going to look at the depth map input and output, and that's because, well, we did that last week and we noticed that it's just really small. So let's take a look at the vertex shader. Now we're just going to use the exact same vertex shader that we used 2 weeks ago, and so we're going to use the standard projection texture vertex shader that we created 2 weeks ago, and nothing is really going to change on that. And really all that we're doing is we're taking our object, and then we're going to multiply our object by the world view projection, and we're going to get our world view projection matrix. We're going to get our position, then multiply it by the world view projection. We're going to get our world position, and so we're going to get our object position and just multiply it just by the world. And we're going to use it for the x, y, z, and that's going to be used in order to kind of like normalize our normal vector. And we're going to grab our texture coordinates, which is going to be normally as grabbed, and then we're finally going to normalize our geometry by multiplying our normal against the world matrix, and then finally normalizing it. Normalizing it, once again, means is that we're going to be converting this vector to being some kind of like crazy old number, and we're going to convert this number to have a length of 1. And then from that, we're going to calculate our light position, our light direction, and we're going to calculate our attenuation. And then also here we're going to get our projected texture coordinate, and that's ultimately going to be our object position again, and instead of being multiplied against our worldview projection matrix, we're going to multiply it against our projective texture matrix. And then we're finally going to pass that all down the line. Okay, so now let's take a look at the magic in our pixel shader. So it's all going to be taking place here inside of the pixel shader. Okay, here we go. The occlusion projection texture pixel shader. If that isn't a crazy amount of words, I don't know what is. This is like the world's biggest name. But we're going to start off by first initializing our output color to 0. Just make sure that it's a float for, and that we're initializing it as black. All right, then we're going to take our light direction from our input, and we're going to normalize it again. We're going to get our view position by taking our camera position, subtracting our world position, and then we're going to normalize the result out of there. We're going to get our color sample, which is actually coming from the black and white texture, and we are going to sample our texture color at that time, and then we're also going to sample our ambient color. We're going to take all that information, we're going to plug it into our light contribution data, and then we're going to plug that into our convenience function where we're going to get our light contribution, and this is going to give us the amount of diffuse light and the amount of specular light that we're going to deal with. And so we're actually going to calculate what our red, green, and blue colors by just simply adding them together. It's going to be our ambient light plus our in-dot attenuation times our light contribution. Remember, the result of our light contribution is it has the, I believe it's the X channel has the diffuse, and the Z channel has the Z channel has the specular component. And then we're going to make sure that the alpha of this is 1, so it's nice and opaque, because we don't want to deal with this. Now here comes the magic where we're dealing with our depth map. Okay, we're first going to test to make sure that the projected texture coordinate W, we're going to make sure that it's greater than 0. Because if it's less than 0, that means we know that the texture or the object isn't going to have the texture coordinate, it isn't going to have the shadow map on it, so we're not even going to worry about it. So the first thing we're going to do is we're going to get our in-dot projected texture coordinate, and then we're going to take the X, Y, Z components of those and divide it by the W. And so what that does again is it puts that into NDC space to make sure that we're in the right space and the shadow is being projected properly on here. Then we're going to grab our pixel depth, which is nothing but our projected texture coordinate depth, and we're going to subtract it from 1. And then we're going to use that information from our projected texture coordinate, and we're going to grab that, but not from our our projected shadow. We're going to grab it from our depth map, and that's going to give us our sample depth. So we've got our pixel depth and our sample depth, and so we're going to say our projected color. Here's where the magic is. The projected color finally is going to be, if our pixel depth is less than the shadow depth, then we're going to color it white. Otherwise, we're just going to give it the projected color of our image. So we're just going to leave it exactly colored the way it is. This is a ternary operator, in case you're unfamiliar with it. Notice that it has a question mark and a colon. Everything to the left of this less than sign is going to be, or left of this question mark is going to be an expression. Now, if this expression evaluates to true, if the pixel depth is less than the sample depth, is the sample depth actually closer, then we're going to color it white. That means we're just going to color it as is. However, if the shadow map is closer, then we're going to color it the actual background color. So we're either going to be color it the shadow color or the background color. And then we're just going to take the result of that and then multiply it against our output color, again, where we've got that going. So ultimately we're going to end up with either the normal texture color, or we're going to end up with a shadow of black. And that's exactly what we have here. Notice here, as we kind of fly around, that the projection kind of like goes through, and our projection is on the surface, and we have our teapot right in front of it. Because the teapot doesn't change position, the teapot stays in its relative position the entire time. Now, mind you, we could, just to prove that this is live, eek, come on. I love Shader Tool, but it doesn't have the most dynamic performance interface available. Okay, so notice that the teapot, as I'm moving it back and forth, kind of like moves where it gets occluded around here. Oh yeah, I've got this just in case we wanted to take a look at that. Okay, now there we go. There it is, gang. That's where the teapot is, right in front of us. If we just fly our camera around, we can see our teapot right in front of there, and notice that the teapot is now occluding of where the projection is actually landing on our surface. And there you go. And of course, where we're looking at it, of course, the camera and the light are situated right on top of each other, so we can't actually see the occlusion here. But if we move our camera around and we leave the light exactly where it was, then we can actually see where the projection and where the occlusion is taking place. So cool stuff, gang. All right. So let me move this on forward. All right. Okay, so that's the occlusion map. And so really, it wasn't that much of a distance. All we did was bring in our depth map, and then we rendered our object as normal, and then we compared our distance from the depth map. And if one was larger than the other, then we colored the surface whatever our shadow map color was. Otherwise, we just left it as is. Nice and simple. All right, now the next step is to deal with kind of like, we're going to kind of invert it, kind of like make it inside out. But otherwise, we're going to use the exact same concept. Nothing new. We're going to render the scene as the scene from the perspective of the light, and we're going to store it in the render target, just as we did there. And then we're going to render the scene again from the perspective of the camera. And now we're going to use the depth map to determine if the geometry is in shadow or not. Okay, it's a nice, simple little calculation. And so it's really just it's really just the exact same formula, but just kind of instead of returning white, we're going to return black, and everything else is going to return white otherwise. So it's really just the same algorithm. It just kind of like flipped inside out. The results of this is where we're going to modify the specular and the diffuse, and we don't want to modify the ambient. So that's why we have the ambient as a separate color. So we're going to multiply the result here only against the specular and diffuse. Because remember, ambient is the color of your scene that is in shadow. So that means whatever's in shadow will be the darkest element. And ultimately, you don't want your shadows turning black, because that's bad. But your shadow should be done. So that's why we're not multiplying the result of the depth map against our occluded depth map against our image, because we want the ambient color to come through. Okay, and then we have our sample depth, and that equals the sample of the depth map at the projected texture coordinate. And then we have our pixel depth. So we have the exact same comparison again, gang. It's the exact same result. If we have our pixel depth, and then is it smaller than the sample depth, and that means that the pixel depth is closer to the camera, then we're going to return a value of black. Otherwise, we're going to return a value of white. Okay, what does that mean? Okay, we're going to take that white and black, and then we're going to multiply that against the light contribution, which is the specular diffuse the specular and diffuse value, and we're going to multiply that white or black against that. So that means it's either going to be in shadow or it's going to be out of shadow. And move my mouse over here. Okay, so let's take a look at the results of this inside of our demonstration. Move this on over here. Okay, there it is, gang. There is what our object looks like. This is with our teapot projected, the shadow projected from the teapot onto the surface as seen by the light. Notice that this is where it's projected on here, and we don't actually see the teapot. Why don't we see the teapot? Because the teapot is a separate object, and so that's why we don't see it. And so let's take a look at our shadow map here. Okay, is this it? Okay. Depth map, okay, exclusion, oh, here it is. Okay, now this should look very, very similar because it's the exact same shader as the original occlusion map. And the only difference here is when we come down here and then we did the test to see if our projected texture coordinate value, if it's greater than 0. Then we do the exact same process as this. We've got our texture coordinate, we put it into NDC space by dividing through with our W component. Then we have our pixel depth, and then our shadow depth. Remind you, our shadow depth is now coming from our shadow map. Oh, that's right. And in order to create a difference, I did say that, okay, instead of a depth map, now I'm officially calling it a shadow map. So that's why I have an extra an extra texture in here. Now notice that for the sampler on my shadow map, I'm not leaving it like the depth map. It still basically has the same addressing. It's still border, address U and address V, and it's still the border. But if you look in here, the border color, now I want it to be colored as black. And now that is going to see that, okay, if the object is, remember I had to do special consideration, and then my whole image is inverted. Now for other folks' system it might be white, but for this it's going to be colored black because I'm going to take the inverse of the shadow map texture, and so that whatever is white or black is then is going to become white, and whatever is white is then going to become black. So we're going to be dealing with levels of black multiplied against there. Okay, with that done, we've got our shadow map, and so now we're going to go here. We're going to go our shadow map. Okay, we have, okay, so we have here, if our pixel depth is less than our shadow depth, then our shadow color is just going to be black. However, if our pixel depth is greater than or equal to our shadow depth, we're just going to color as white. And then here we're going to do is just take our light contribution and we're going to multiply it by our shadow. And that's really all that there is, gang. Because otherwise it's the exact same thing. We have our out.rgb is going to be our ambient plus our attenuation times our light contribution. And then we're going to just make the alpha a value of 1. And so really it's almost the exact same shader, except instead of returning white where we saw the depth map, we're going to return black. And otherwise we're going to turn white wherever there is shadow. And so that's going to produce our image. So what does this look like when we bring it in? Okay, here it is. I rendered my teapot and I put a nice little Mandelbrot set texture on it. And now we see here is a projection of the light, of projecting it onto our teapot. And we pushed our teapot really, really close, or it's actually the teapot is really, really far away from the box. And so that's why it's casting such a huge, humongous shadow. So let's actually move that a little bit closer. Let me fix my camera. Okay, where is my... It's going to be around here someplace, gang. Yep, there it is. I can't remember where the control is, but I'm not going to move that around. But the reason why it looks so darn big is because we moved the teapot far away in order to get a more pronounced depth map. Now notice here that the back side of our teapot is still dark, and that's because it's not receiving any light. And so it's working well, and it's complementing here. Now also notice here that our shadow is not black, and that is because we're only multiplying the shadow color against the diffuse and the specular components. The ambient color stays the same. So that's why we can still see a little bit of the background or a little bit of the natural source texture right on through, is because we're not multiplying the ambient color by the results of the shadow map. Pretty cool stuff, and really not that more complicated between that. So that's why we kind of wrap things up and combine them together into this one lecture, because really they're almost the exact same. They're almost the exact same shader. Really, really awesome stuff. Well, if you liked what you saw today, that's all I wanted. That's all I had to show, and that kind of like wraps things up all together. But if you like what you saw today, go ahead and subscribe by clicking on the little subscribe button in the lower right-hand corner. And otherwise, my name is Chris Rhoda. You can check me out on Facebook or on LinkedIn, or you can go check out Art EDU, which is also on Facebook and on LinkedIn. Okay. Thank you very much for joining us today, and thank you very much for dealing with all of the craziness and the nonsense, and then dealing with all this HLSL stuff. And I look forward to interacting and showing you more crazy old tech art stuff from another episode of Tech Art Talk Live. And until then, arrivederci.